Hello everyone, my name is Antonio Davoli and I'm a production engineer at Meta. Today, together with Leandro Silva, we are gonna present you the work around hardware and software remediation at Meta. Meta, as probably many of you already know, owns a family of applications that are pretty famous and pretty large, like Facebook, Instagram, Oculus. Think about the numbers that these applications run every day and the amount of customers that they serve in a daily basis. Consider the amount of traffic that this application need to serve. We do have employed more than 15 data centers that are distributed geographically. So every time someone hits, like scroll his Facebook page or check his Instagram feed, it will be directed in one of those machines in our data center where the load will be served. Everything would look fine, right? So we can just simply add more machines and hope that everything works for the best. That's actually not enough. What we need is some mechanism in place that can help our fleet to stay healthy every time. And this is important for us and for our customers. So what we need to exploit here is something that can detect, fix, and mitigate both hardware and software problems. Let me just give you some numbers. Every day on Meta, we execute more than 5 million software remediations. What do I mean with software remediation? So for us, these are software actions that often are written by our customers, and they have the final goal of checking if the services that run in this device that we have in the data center, they work fine. So they are the one they are capable of bringing back the services if something doesn't work as expected. And we do have like quite a bit of them, as you can see. And similarly, we run always in a daily basis more than 5K hardware remediation. Those are like slightly different type of workflow because in this case, what we're going to do is to be more invasive with the kind of operation that we execute, because what we want to do in these steps is checking if there is some problem with the hardware and bring the machine back to production by spotting the problem behind, fixing the components if needed, and so on. That's why they are like more invasive, because we are going to try more invasive operations like rebooting, reprovisioning, and stuff like that. So this is just like the platform that we use internally, and it's exploited every day by more than 100 customers. But what I want to do now is to give you a small overview of how the entire pipeline works. The overall architecture looks like the following. Let's take one of these machines is deployed in our data center, one of the 15 I was telling you before. What happens is that constantly we have a detection mechanism that is in place to evaluate in a cadence, and Leandro will give you an overview on that in a very short while. The detection will check if the machine is fine and if the services they're running in this machine are operating fine. If something happens here, the detection system will raise an event. The event is then picked up by a platform that is in charge of software remediation that I was telling you before. And here is going to be our first line of defense. If the mitigation here are successful, we are able to send the machine back to production where it can start to serve traffic again. Otherwise, if there is a problem, or if for example, the underneath problem was related to the hardware, what we need to do here is to escalate to the hardware remediation platform. Here, as I was saying before, is where we are going to be more aggressive with the type of operation we execute in order to validate that the hardware is healthy, fix components if they're needed, and send the machine back to production. So this is what is going to be about this talk today. Leandro and I will give you an overview of the entire pipeline, zooming in its main component. So Leandro will start in a very short while to give you an overview on how detection and alarm generation work. Then I will come back and explain to you how FBAR actually works and how we treat software remediation of Meta. And then we're going to move into back with Leandro, where we're going to have the introduction to hardware remediation and few hints on what's going to be the future work. And with this, I'm going to pass it to Leandro.
So thank you, Antonio, for the introduction. And now let's dive into the detection. As Antonio pointed out earlier, detection is the first stage of this remediation pipeline. In order to make sure that this remediation pipeline works as efficiently as possible, it's critical that we have a really good detection mechanism in place so that we can identify whenever servers are at fault or not. So as you can imagine, in order to support our various apps, we have multiple servers spread around the globe. And in order to understand a little bit better how the detection works in practice, let's dive into one of these devices and see what happens under the hood. So basically, we have an on-host detection agent that's periodically running in every single device, which is responsible to assess its health condition. So we will verify things like the state of the CPU, the memory, network cards, and depending on the condition that either of these components are found, we will deem if the device is worth for serving production traffic or not. At the end of this assessment, the result will be in a form of an alarm, which will later be picked up by FBAR. And then we will have Antonio go back and he will dive into the details of what happens with these alarms generated by the detection pipeline. But here, what's important to notice is that we have this widely distributed binary running across every single device perform these self-assessments. As you can imagine, this imposes like lots of challenges for us. And in order to optimize this, we decided to also have an on-demand periodic assessment. So in addition of the on-host periodic detection, we have an on-demand assessment as well. This flow is meant to be used by either humans or automation later into the repair workflow, which is responsible to ad hoc and queue a request to perform a health assessment that will be carried through a worker, which will remotely perform the series of checks against the required device. The main difference here from the on-host detection is that all the checks are performed remotely instead of being performed locally within the host. So with this flow, it allowed us to push code faster and also avoid high usage of resources within the host. And with that in mind, we decided to scale up this platform so that we could also carry through the periodic health assessments remotely instead of doing everything locally. So for that, we introduced a scheduler, which means responsibility is to constitute an inventory for all the servers available that should have its health assessment performed. All these requests are in queued and then picked up by this worker, which will again carry through the same mechanism as we saw previously, remotely verifying all the state of these components against the required devices. Once these executions are done, the ending result will be in a form of an alarm, which will later be picked up by FBAR. In this way, it allows us to scale better because we can now just push the new code like to the scheduler and the worker and not necessarily needing to rely on deploying a widely distributed binary across all the servers in the fleet. So with that said, I will now hand over back to Antonio, who will go into the details of how FBAR processes these alarms and what works under the hood on that side of the pond. So with that said, I'm handing over back to you, Antonio.
And thanks, Leandro. Now it's time to introduce you to FBAR and the world of software remediation. The pipeline that we have been describing, we are now tackling software remediation. So let's zoom in and see what happens. FBAR is the product that we use for dealing with software remediation. The acronym stands for Facebook Auto Remediation System. And it's a platform that we expose to our customer to write custom logic, so they can write piece of code or function or modules if you want. And we expose them a mapping between this function and an event that can be raised. FBAR will be in charge of executing this particular remediation or this particular action whenever that kind of alert will be raised. So we expose this as a service for our customers, and they need to just focus on the remediation logic, and we'll take care of everything, in deployment included. So FBAR is not a brand new tool. It was introduced first in 2011, and its architecture back then was slightly different from the one that we have in place today. So if you go and read the initial blog on the engineering website, you will see that the FBAR architecture that's described there is pretty simple, but it did its job. So at the time, it had a basic module for fetching events from the events database, let's call it this way, and putting these events into a queue. And the remediation will respond in according to the events that were placed in the queue. And that's it. Like it was working. It was kind of doing its job, but it was painful for us to maintain, especially because the remediation code was in a single code base, actually in a single service, was pretty much a monolith, if you want. So and this was painful for us, especially if you consider like the maintenance when we had to deal with more customers, like a different use case, because this like something happens every time. You have a customer that comes and have a particular use case, and you want to facilitate his onboarding. So it's important to scale with the application. So the first step that we've taken to modernize FBAR has been to extract the remediation logic and put it in service of their own. Customer can now just deploy their new remediation or change the existing one without touching the engine itself. This is handy for us because we don't have to take care of the logic related to the remediation themselves. And it's important for the customer because we don't have one customer, for example, landing a broken piece of code, they can break the entire operation. And this was fine. This actually worked well and served well many of our customers. But we want to go faster. We want to provide like better timing for speeding up and creating those remediation. That's why the next step that we are taking was to take the central piece where we do the orchestration and split it in microservices. The initial version of those microservices was written in Python, but to comply with the performance that we need in our architecture, we are migrating them to C++. So many of them are already written in C++. This gives us more performance and is giving also our customer a better FBAR. So what are these microservices that are now in place? They substitute the old monolith. And there is one for like taking a lock for one of the remediation that needs to go through. So we want to ensure that only one remediation run at the time against one machine. We want to check the configuration files in which the customer express the mapping within remediation and event are updated. So we have a service that behind the scene checks those configs and makes sure that we always run the latest version of the remediation. And finally, we have a service that is in charge of rate limiting the remediation. Because the last thing you want is too many of those remediation into your fleet at the same time. So this is a service in place that allows customer to set limits in timing of, for example, I want to run 5 remediation in 60 seconds. So they can specify a time interval, the number of remediation, and this is the contract that they maintain with us, and we are going to deliver in making sure that it is maintained. So this is actually the FBAR architecture that is in place today. And as I was telling you, is the focal point of dealing with software remediation. But when one of the software remediation fails because the issue was with underneath hardware, we need to escalate, as I was telling you before. So now I will pass the ball back to Leandro. They will explain to you what happened when we have to escalate because this is a problem with the hardware. Thank you.
Thank you, Antonio. So now let's dive into the repair brain and see how hardware remediations are carried through for any of the fallouts that are not resolved through FBAR. So just to remind ourselves, we are now at the very tail end of this remediation pipeline, where we are going to perform more invasive actions in order to return this capacity back to production in a healthy state. So in order to achieve that, we have repair brain, which is basically the decision engine of the repair workflow. Here we can think of all the actions that can be carried through for a particular bad condition are known to the system. So that knowledge could come in either of two ways. One is through a series of configuration actions that are inputted by hardware experts, where we would have a mapping of, for every bad condition, what series of actions can be attempted in order to recover that capacity. So for example, for condition A, we may try to perform actions X, Y, and Z, and repair brain will be responsible for carrying those actions through, recording its state if they were successful or if they failed, and then checking with the on-demand detection framework if these devices are now deemed healthy or not. So you can think of after every action we are iterating through, we will check if that particular remediation has resolved the condition or not. In addition to that, we can think of for cases where we are not able to resolve the condition automatically by the automation, we will escalate that to a data center technician, which will then perform additional troubleshooting and additional actions in order to resolve it. As you can imagine, this is not a very efficient pipeline because we have limited resources for humans that can be performing this troubleshoot. That's when we employ the machine learning model, which is main responsibility is to learn from what actions have been performed during this flow for a particular problem in order to tie them back so that whenever this problem occur again in the future, we can easily carry through all these actions given by the model instead of having to hand that over to a human to perform additional troubleshooting steps. This machine learning model is by no means perfect. Like right now, we have ongoing challenges within its accuracy. So it's a trade-off of how much we let it run autonomously, learning from all the bad conditions and successful and failed actions versus the actual resolution of these problems. So with that said, we have in our hands right now everything that composes this remediation pipeline. As Antonio started on the discussion, painting out like how it looks like, we went all the way from the detection where everything starts, then later to F-bar where some software remediations are carried through, down to repair brain where we take like a more invasive actions in order to recover the capacity back into production. With that said, would like to invite you to have a look at the future work that we have laid out for this area. And we welcome if you could join us and help build upon these solutions. So to give you an idea what we're looking after, one, it's faster detection. So we want to be able to minimize the risk where production workloads are running on unhealthy devices. So for example, if we can reduce, we can be faster at detecting that a particular device is suffering from a bad condition from 30 minutes down to a couple seconds or minutes. It's less risky for the software applications that are running on that device because we can drain them, repair, and bring them back quickly. Also, we have generic remediations. So far, we have been historically acting upon a category of assets, which are servers or network switches. And now we would like to be more granular and provide more flexibility to our customers so that we can tackle workloads such as top-order tasks and also, for example, BMC devices to hint some of the things we will be looking at. And lastly, but not the least, is higher accuracy. Within all this pipeline, we really need to make sure that all the actions we carry through are the most precise as possible so that we avoid wasting parts when the swap was not required, and also minimizing the time which these devices are outside of production. So we perform just the necessary amount of actions in order to bring the device back to a healthy state. With that said, I would like to thank you everyone for listening to Antonia and myself. If you have any questions, please feel free to reach out to either of us or any of the employees at Meta. And if you found any of this interesting to you and you would like to help us build a really scalable and efficient repair pipeline to support our various apps, just reach out to one of us. We would like to have you on board in the team.